I can show you. So here it is the loop. This whole loop could be simplified with single order transfer function. Okay. So now we have uh, reduced our this current loop, and the remaining function, the remaining thing which can be seen in here. So our current loop is this inner current controller loop can be reduced to single order system, single order transfer system. So the remaining thing will be this PI, this plus this motor's mechanical transfer function with a filter. Now we can design our this speed controller here. So let us get started. So you need to remember this. Let me open a new file. You can just scroll back and just see what had happened. So let us start with a new page. Okay. So I'll draw this function. Draw the speed controller. So here it is your an reference signal which is compared to your measured signal. So measured speed. This will be passed to a PI controller, a speed controller. So we can write it as to be K, uh, KS, maybe. Let us write as to be KS because this is a speed controller, so it will be KS 1 plus TFT. TSF. TS is the time constant of this speed controller. This will give you IA star, IA reference signal, and we can now write this as to be KI over 1 plus SPI as was solved uh, while we did our current controller in the current controller design. So in our current controller we designed our PI controller. So when this IA goes, then IA can be multiplied to KE by B over 1 plus SPL, mechanical time constant, and this will give you your speed. This speed will pass through a filter. Let us say H omega upon 1 plus T omega f, and this will go here. Now the same thing which we did for the current controller design, same thing we have to do for this speed controller. So we know these things we know, but we don't know this Ks and Ts. We need to optimize this Ks and Ks value. So how to do that? Uh, Same thing we need to proceed. We'll calculate our GSHS of this loop. So it will be, let me scroll down. Okay. So here it will be Ks. Let me take out all the constants. Ki, Ke by B, Ks, and there will be H omega as well. With that again. Then all the poles could be taken. there is 1 0 as well here. Okay, this is our transfer function. Not transfer function, just GSS. So we could take our time constant of this speed controller to be equal to uh, one of these, maybe Ti or T omega. Uh, but if Ti is the current controller time constant, so we should not take the current controller time constant as to be equal to speed control time constant. And also this Ts should not be equal to this T omega as well, because this filter constant is also very less. So whatever we do, this system will be reduced to a third order system. But we know to optimize a second order system by equating your zeta to be equal to 1 by rho. So uh, in a third order system, there is a separate method of symmetric optimization. Uh, so let us do that. So what we do in symmetric optimization, we calculate this GSS. We calculate this GSS and then the transfer function of this omega nm upon nm star. And then it is equated to, it is optimized to maintain a gain of 1. Because as we have already discussed, the output should always track the input. So when the output is always equal to input, then the transfer function has to be 1. So we will optimize the this transfer function such as the value is nearly 1. So let us do that. Let us first reduce this system to as minimum as we can. So first approximation which can be done is 1 plus, sorry, first approximation that can be done is SPM is equal to SC, because in the range of this variation of the input frequency, this one can be neglected in comparison to this high time constant. So 1 plus SPM can be equal to SPM.